Hello, this video focuses specifically on conservation of mass. The essential question is, what is mass and how do we measure it and track it in systems? So mass, as you may recall, is an important fundamental physics variable. We use the letter lowercase m to represent mass if we were going to use it in an equation, for example. And mass for a physicist is defined as the total amount of stuff, electrons, protons, neutrons, inside an object, regardless of its shape, size, etc. For you guys, you've probably your whole life been using that word or hearing that word, and it's basically how heavy an object is. Although that's not quite true for physics, because if you were in outer space, it wouldn't feel as heavy. But that doesn't mean it doesn't have the same amount of stuff. So mass is specifically the amount of stuff inside of something. The typical units physicists use, again, are kilograms, abbreviated kg, pounds, which is lb, or sometimes grams, which is just a g. For your own common knowledge, because we use pounds in America, you all probably know like how much you weigh in pounds. We want to get a little bit more familiar with the concept of kilograms. So in general, a kilogram is about the weight of a pineapple, which is more than a pound. It's about 2.5 pounds. So when I say 1 kilogram, I'm talking about pineapple. Picture yourself holding an average, everyday, normal-sized pineapple, and how many pineapples do you think you weigh? I'm about 65 pineapples. So that's kind of a translation in your brain from pineapples to kilograms, which might be helpful because that's the unit you'll be hearing me use in this class more often. So mass is one of our conserved variables, and if we wanted to talk about conservation of mass, we could use a closed system. This is a closed system of Legos, which exists in my house all the time because I have a 4-year-old and a 6-year-old, and they are constantly breaking, making Legos, putting Legos on the floor, underneath my feet, all the things that many of you guys probably grew up with as well. But Legos are a great example of a closed system. So if one day ago I had 200 Lego pieces and I imagine them in a closed system, that means nothing can go into that pile, nothing can come out of that pile, but the shape of the pile can adjust. So I had 200 Lego pieces. Each one of them had a mass of about 2.5 grams. So if I wanted to know how much mass was in my system a day ago, I could calculate sigma mass would be about 500 grams. Today, I could look at the same Legos and my kids would have built amazing inventions out of those Legos. We now have 10 Lego structures they've built, and if each of those structures is 50 grams, you'll see that sigma m for the Legos is still 500 grams. No matter how the Legos look, if I put them on a scale and measure them, the mass hasn't changed. So this is true in any closed system. Sigma m is always going to be the same. We're going to have the same mass before as we have after if we're talking about a closed system. All right, let's do an example of how we would see mass being conserved or tracked in an open system. Let's assume we have a system that starts with a cup and froyo in it. So we're at the froyo store, someone handed us a cup that already had the froyo in it. That's my system now. Now, probably you might want to add a few things to that. For example, maybe I'll add 20 grams of gummy bears and 30 grams of hot fudge. You'll notice that I don't know how much the cup and froyo, what the mass of those were, and I don't even care. What I care about is what's going in and what's coming out. So I'm going to start off just not knowing the cup, but knowing all the things that are going in and out. Once I put those things in, I'm going to take out negative 230 grams of assorted delicious froyo with toppings. I'm probably going to eat it. You'll notice that I put a negative sign on there. That's to indicate the fact that that mass is coming out of the system. It's okay to have negative mass if you're losing mass. So the analysis of the system is as follows. I would calculate delta m. I can't do sigma m because I don't even know the mass of the cup and froyo, and also sigma m only applies at a single moment in time, and we have this stuff happening over the course of the day. But I can do delta m. So the change in mass of that cup starts with a froyo. We add 20 grams, we add 30 more grams, and then we take away 230 grams. And so we end up with an overall delta m today of negative 180 grams. That tells me that this cup is losing mass overall, which is true because we're taking out more than we put in. Usually we don't use sigma mass in open systems because it's changing every moment, right? As we take each bite, the sigma mass is changing. But it is important to note that even though the mass did leave this system, it's not like it disappeared from the universe. It just moved into a new system, me. And if you took the mass of myself before and after I ate the froyo, you would discover my mass went up by 180 grams to compensate for that. So the universe as a whole keeps the same amount of mass, even if it goes in and out of individual small open systems. Okay, we're at the last slide. Please take a few minutes and revisit the essential question. What is mass? What does it mean? And how do we measure it and then track it in different kinds of systems? Thanks for watching.